Have you ever stopped mid-game and just wondered, how is this even possible? 100 real players running around a massive, dynamic world, all synchronized in real time on your phone? I mean, if you just look at the numbers, it seems completely and totally impossible. So today, we're going to pull back the curtain and look at the incredible, mind-bending engineering that makes it all work.
Everything, and I mean everything we're about to talk about, starts with this one simple number, 100.
That is 100 different people, in 100 different places, on 100 different Wi-Fi connections, all needing to see the exact same world at the exact same time. Just syncing up that many human beings is a monumental challenge, but believe it or not, that's the easy part.
Because it's not just about the people. Now you got to add this number into the mix, 40,000. We're talking about every single weapon, every bullet, every vehicle, every door that can open and close. Each one of those 40,000 things has a state that the server needs to keep track of. So you have 100 players constantly changing the state of 40,000 objects. This is the impossible premise. Mathematically, it just shouldn't work. So how on earth do they pull it off? Well, the very first problem you have to solve is what I can only describe as a data explosion, an absolute tsunami of information. With so much going on, how does a server not just, melt under all that pressure? See, if you did this the simple way, every time you took a single step, that little piece of information would have to be sent to all 99 other players, and all of their movements would have to be sent to you. This creates what engineers call an O of n squared problem, which basically means the data load blows up exponentially. With 100 players, you're looking at something like 300,000 updates a second. There is no server on Earth that can handle that. It would just crash and burn. So the solution isn't to throw more power at it. You have to get smarter. And this is where the real magic happens. It's a system called the replication graph. Instead of shouting out everything that's happening to everyone all the time, the server cleverly breaks the map up into a grid. Then, it only tells you what's happening in your little square and the squares right next to you. It's kind of like having a personal spotlight that follows you around, only illuminating what you actually need to see. And the difference in efficiency here is just staggering. The standard brute force way means checking all 40,000 items for every single player, every single frame. We're talking millions of checks a second. It's insane. But the replication graph, it's surgical. It takes that massive workload and shrinks it down to maybe, just maybe, checking the 50 or 100 items right around you. This one brilliant idea is the bedrock that makes a 100-player game even possible. Okay, so we've tackled the problem of data quantity. But what about the speed of that data? This gets us into the territory of latency, or as we all know and hate, ping. The thing is, because of the actual laws of physics, there's always going to be a delay. The time it takes for your action to travel to the server and for the server's response to get back to you, that's a real physical limit. So if there's always a delay, how does the game trick our brains into feeling like everything is happening right now? It pulls off this illusion with two incredibly clever tricks. First up is client-side prediction. When you press the button to move forward, your game doesn't wait for the server's permission. Nope, it moves you instantly on your screen and just tells the server what you did. It's predicting the most likely outcome. But the second trick, server-side rewind, is what really bends your mind. And this explains one of the most frustrating moments in all of gaming. You know the feeling, right? You swear you made it behind the wall, but you still get knocked down. That's server-side rewind at work. When an opponent shoots at you, the server doesn't care where you are now. It literally rewinds time to the exact moment they pulled the trigger and checks to see if their shot lined up with what they saw on their screen. It's a necessary trade-off to make shooting feel fair for the shooter. But of course, there's another layer of chaos here. We're not just fighting the speed of light. We're fighting something far more unpredictable, the mobile network itself. So most of the internet you use, websites, email, it all runs on a protocol called TCP. Think of TCP as registered mail. It's guaranteed to show up, and every piece arrives in the right order. But if one letter gets lost, the whole delivery chain grinds to a halt to find it. In a fast-paced game, that's a total disaster. That's why games use UDP, which is way more like sending a postcard. It's blazing fast, and yeah, a postcard might get lost here or there, but the key is the mailman doesn't stop. The next postcard is already on its way. So what do you do about the really important stuff? I mean, you absolutely cannot lose the packet that says you eliminated someone, right? Well, for this, the engineers built their own custom system right on top of UDP. They use that fast, unreliable postcard channel for things that update constantly, like your character's position. But they built a special, reliable channel for those critical one-time events, making sure those packets get special treatment and are resent if they get lost. It's truly the best of both worlds. You can actually see how the server manages all this chaos over the course of a match. Think of the tick rate as the server's heartbeat. At the start of the game, with 100 players dropping into one tiny area, the server is under incredible stress. Its pulse is low, maybe a bit erratic. But as the game goes on and players are eliminated, the load lightens and the server's heartbeat gets faster and steadier. This is exactly why that final 1v1 circle feels so much smoother and more responsive than that chaotic hot drop at the beginning.
So we have all this brilliant software, but it has to run somewhere. And when you zoom out, you find this entire experience is being powered by a massive global cloud infrastructure. What's really clever is how they split the work. All the stuff that happens before a match, logging in, finding teammates, matchmaking, that runs on elastic systems that can scale up or down in an instant to handle millions of players. But the second your match starts, you're handed off to a powerful, dedicated workhorse of a server that has one job and one job only: run your game flawlessly until there's a winner. It's like having a giant waiting room separate from thousands of private dining rooms. And underneath it all, there's some incredible hidden tech making things better. They use special servers called Graviton that are built on the same architecture as your phone's processor, making them way more efficient. To keep your ping low, your data doesn't just travel on the public internet. It gets routed onto a private superhighway that bypasses all the usual traffic jams. And they use a high-speed data pipeline called Kafka to analyze game data in real time, which helps them catch cheaters almost instantly. So when you put all these pieces together, you get the blueprint. You can see it's not one single magic trick. It's this beautiful stack of brilliant solutions all working together. A custom network for speed, a grid system for scale, illusions to conquer latency, and a global cloud to power the whole thing. Each one of these pillars is absolutely essential to making that impossible premise a reality.
And that, of course, brings us to the big question. If this is the incredible level of engineering required for the 100-player games of today, what comes next? As we start thinking about even bigger, more complex, more persistent real-time worlds, what will the next generation of this technology make possible? Because the solutions we've talked about today, they aren't just for gaming. They are the fundamental building blocks for the entire next era of shared digital experiences.